Well, it is the top of the hour, I think, and so I am going to get us started here. Ray has joined us in the other room. I'm trying to get the, let's see, there we go. Get everything set up here. And so I can go ahead and there, I can hear myself now. Hello, welcome to the show. I'll let Ray start get set with sharing his PowerPoint, and then I'll say hello to him. If he's not able to do that, then we have alternative issues. Thank you for your patience. The couple of you that started with me at the bottom of the hour, I seem to have made a mistake when I saved that slideshow for tonight that I had worked so hard on. I'm going to put it up as a separate video. I'm going to remove the meeting information and just put it up because it's a bunch of pretty pictures. And let's see what else. Steve Kaminski, Mike Webb, maybe writing Bidicapher. I apologize. Ken Elliott and Annalena Seed Hill, thank you. I'm slowing down here. All right, I need to slow down. All right, this is the September meeting of the Pinal Geology and Mineral Society and the Pinal Geology and Mineral Museum in Pinal County, Coolidge City of Arizona. And I'm going to pop Ray on here and so he can say hello too and tell me if he's got any technical problems like I've had all evening. So there's Ray.
Good luck. Yeah. No, I just need to have you take me through it. So.
Oh, okay. We're having that. Your microphone's a little weak.
Okay, let me.
Maybe mine is too. I'm not sure.
Is that better? My voice, it's allergy.
When I shut up, yes, it will be much better.
Okay, I get it up all the way. So I'm going to open PowerPoint, right?
Right. Open PowerPoint and start the slideshow.
Now I'm going to hit slideshow.
Right.
And then I'm going to pick setup slideshow.
No, shouldn't need to do that unless you've been playing with it since last night.
No, it changes automatically. So I've set up what I want to do, individual window.
Yep.
Yeah, see, it changes automatically back to something else.
Okay. Mine doesn't. All right, and then start slideshow.
Okay. So what do we see?
We don't see anything till you share it. You have to go back into the browser, go Chrome.
Chrome, okay.
And at the bottom of the screen, hit share.
I can't find share. Let me see. Okay, share, got it.
All right.
Video file, share screen.
Share screen.
Okay. Share screen.
Hopefully share application.
I hit entire screen window or Chrome tab?
Window, excuse me.
Window, okay. Share. Oh, then I hit PowerPoint.
PowerPoint's the one you want.
Yep, then I hit share.
Here it comes to me, and all right, I see it on my screen, so that's good. I haven't started sharing it with our audience yet. I will do that.
You think we're on? You think we're on?
We're on. Yes, we got a bunch of people sharing their screens, so we've got a lot more than my little ticker says eight viewers. That's what we got.
Have a party, so
yeah, we got enough for a party. I want to let everybody know, in case you didn't, that tomorrow is National Rock Collecting Day. So go out and take lots of water with you. and maybe pick up a rock somewhere. I've even found nice ones in the islands in parking lots. Yeah, I know that's cheating, but if I just want a pretty rock, I could find that. All right. So with us tonight, without too much further ado, is Dr. Raymond Grant, and he is the director and curator of the Pinal Geology and Mineral Museum in Coolidge, Arizona, and he is also the president of the Pinal Geology and Mineral Society. And he may hold many other titles.
Job, let me know. I'm ready to.
Yeah. I don't want it. So I'm going to put his PowerPoint up here so he can control that. And I will let him do any more introduction that he feels he wants to do. And I will disappear from your screen. But Ray, I am here. I will be able to talk to you if you have a question for me. And then I will
hey, Bob or something.
Yeah, just say my name and I'll hear it. And then you can people, if you comment in the comments on YouTube, if you are signed into YouTube, this is for our audience, I will relay them to Ray as I am able. So my picture is going to go away, but whoops, no, that's not what I wanted. My picture is going to go away. There it is. But I will let Ray take it from here and tell us about the geological wonders of Arizona.
Well, I'm glad to see so many people. Hopefully my voice will hold up. Not talking for a year or so, it makes it tough. But we may still do a Zoom meeting or a YouTube meeting next month. I'm not sure. We need to see what happens. I am going to start opening museum on Saturdays in October. I'll send out a newsletter. And I think we can try to have a field trip sometime in October too, if it, gets to be less than 100 degrees out there. So I'll keep you posted on all those things. So
I will also put out those when I get them on social media, including our Facebook page and hopefully on our website as well.
Okay. So anyway, we're off. So tonight I'm going to bring now that hopefully it takes care of all of that. So I put this talk together and I just picked geological wonders. I could have picked all kinds of things and all kinds of different names, and it covers a lot of territory. And so I'm not going to go into depth on any one subject, but if you're really interested, I recommend highly you go to the Arizona Geological Survey website, and they have all kinds of guidebooks and tourist things and places to go, and it's all up there. It's all been scanned, so it's really tremendous. You type in what you're searching for and go there. If you need more information than the little tiny bits I can give you tonight. So here are the 7 things I've picked for tonight anyway. The landscape, because that's what we all see as we travel around. Then a couple unusual things, the fluid volcanic rocks and the explosive volcanic rocks, which I think, a lot of people aren't so familiar with. Perhaps you are in a way, but not under those headings. And then I picked what I figured the 3 absolute world-class geological features in the state: Meteor Crater, Petrified Forest, Grand Canyon. And then, of course, the thing that's really near and dear to my heart completely, the mines and minerals, which Arizona, really is famous for. So we'll take it from there. So the landscape is really what you see. It's what people come here to see. They travel around and they look, and you see things like the picture I have here of the Chiricahuas, or here's the north rim of the canyon. I mean, this is a hard place to get to, but look at that. What kind of a place, amazing to me. The bare rock. Well, there are 3 things that what we see when we travel around depend on. It's the climate, the type of rock, and the geologic structure. Those 3 things really determine pretty much what you're going to see as you travel, whether it's in Arizona or whether it's, in Wisconsin. Those three things are still the things that determine the landscape, the landforms, what you're going to see. So the climate we know for most of us is hot and dry. And so the key to that is that weathering, which is the breakdown of the rock. So you take a rock, solid rock, you break it down into sand, you break it down into clay or mud, is very slow because it depends on water. And if we don't have too much water, we don't have too much weathering. But erosion is fast, and erosion is the removal of that broken down or weathered material. Because a big storm in the summer can wash away the little tiny bit that's changed, the little tiny bit that's weathered. And therefore, if there's no soil, we're not going to have much vegetation, or because of the heat and the dry climate, we don't have much vegetation, but that keeps the, soil from being in place, why things keep moving away. So we have then, as a response to that, as you travel around Arizona, lots and lots of bare rock with almost nothing on it in terms of the vegetation. That was Chiricahua Peak in Phoenix. And, now, if we go up to the White Mountains, it rains maybe in Phoenix 8 inches a year, whatever, something. And in the White Mountains, maybe 20, 30 inches a year. So there's more rain. So there's more weathering. That means more soil is formed. And because it's a little wetter, the plants can grow and they're going to keep the soil in place. There's going to be less erosion. So what do we see? Well, you look out, there's a giant vista. There's no bare rock hardly to see at all. If you got down underneath the trees, you might see some, but the point is the climate is critical. Most of Arizona is dry and hot, and so most of Arizona has, plenty of bare rock. And then something that I really kind of particularly interested or like is the microclimates. So if you have some place in the shade, it's a little bit cooler. And if it gets wet in a rainstorm, the water doesn't evaporate quite as fast. Well, that means it's going to weather a little bit more because water is what causes all the weathering here. The water breaks down feldspar into clay or mud, things like that. So, here's Hole in the Rock in Papago Park. You see the people, they're all sitting in the shade because underneath in the hole, it's cooler. And if there's a big rainstorm and rain gets all through it, the part underneath is going to stay wet longer. Well, that means it's going to weather a little bit more. That means it's going to get bigger. So you can see there are other holes that have started along the side. And if you could come back in, I don't know, 1 million, 2 million, 5 million years, maybe they'd work their way all the way through the rock too. So I call those microclimates. Here's Hole in the Rock. You can see it's shady. It would stay wet longer. And therefore, it's going to weather faster because it's wet longer. And therefore, the wind blows, the rain washes the weathered material away, and the hole will constantly get bigger. So that's what we see. Some people call those taphonies. You can look that term up, but a hole in the rock probably works just as well as taphony. But in case you want a special name to impress your friends and relatives when you take them there. Another situation similar is something, the Australian word is nama, and the namas, and some geologists in the U.S. use that term too. It's a depression. Water collects in the depression. You can see in the picture. So what's happening in that depression? Well, that water is reacting with the minerals. It's weathering them. And the longer the water stays there, the more the weathering will take place. Eventually, whatever sand, mud, clay is released from the weathering will get blown away or washed away, and the hole get a little bit deeper. And, again, if we could come back in some millions of years, that hole could be several feet deep. So I call those microclimates, places that stay cooler and wetter. And then we look at things like arches, and I have a feeling that this place, that it might have actually started at the top, as a nama, as a hole, or as a hole in the rock. but it's very similar. And so uh, the shade, the weathering, is a little bit faster, and we end up with something like that, like an arch. Excuse me. And then pedestal rocks would do the same thing. It's under the rock, it's shady. So what does that mean? Well, that means it stays cooler and wetter under the rock. Well, what does that mean? That means it weathers a little bit more and it'll disappear. Of course, a lot of pedestal rocks, the material underneath is not as resistant. It might be a softer material or something. It might, weather and erode faster. But it also helps that the climate underneath the pedestal is a little bit different. The second thing, besides climate, is whatever kind of rock you're looking at will determine how it looks. I just put in this picture of the Verde Valley. I'm standing on metamorphic rock. It's hard to see. It's down at my feet. And I look across, and it's all sedimentary rock all the way across until I get to the other side, and there's the San Francisco Peaks, which are, of course, igneous. So, those are the three main types of rock: sedimentary, igneous, and metamorphic. There are three main kinds of sedimentary rocks that we see. There are other kinds, but these three are the most common: sandstone, limestone, and shale. If you have sandstone or limestone, you get a cliff in arid region. The climate's important. If you go to a place where it rains a lot, the limestone dissolves away and forms valleys, forms depressions. It's gone. So we need the climate plus the rock type here. So sandstone and limestones makes cliffs. Shale makes the slopes, as you can see here in Monument Valley. Or you can go to the Grand Canyon, lots of cliffs and slopes. Everything you see in that picture is limestone, sandstone, or shale pretty much. And, you can see what makes cliffs, what makes slopes. Igneous rocks, and we'll look at some more when we talk about the volcanic stuff, but I just picked out one: granite. We have some really neat granite that weathers spheroidally. This is along Interstate 10 by Benson, Texas Canyon, it's called. Here's the story again. The weathering takes place under the ground. The water gets down in the cracks. You can see the pictures where the black cracks are. The water changes the feldspar to clay or mud, and it erodes away. A lot of people think that, if we go back 10, 15,000, 20,000 years, we had a much wetter climate here. It was the ice age over the world. And during that wetter climate, we would have had a lot more weathering. And so the water would have weathered around all these different granites. And then as the climate dried out, all of that weathered material got washed away, got eroded away. And so we end up with this, the spheres. This is a picture of diabase igneous rock in Salt River Canyon, and it shows it real well how the weathering is moving in. You can see the stuff that's partially broken down, and then the good, solid, unweathered material, in the center of this, what's going to be a nice round boulder if the stuff on the outside gets washed or carried away. And because this is a Pinal Geology and Mineral Society, I try to put in, when I could, examples from Pinal County. So on the Florence Calvin Highway, we have the area called the Granites, and you can see there we have these really nice rounded granite boulders. It's a pretty neat area. If you've never gone down that highway, it's worth a drive just to see them. Now, that doesn't always happen. Here's a granite hill. It's over by Coolidge, not very far from the museum. And you notice there's nothing spherical at all. So it didn't have the right cracks. It didn't weather right. Had a different composition, different crystal size. Something was different about it than the granite down on the Florence Calvin Highway that weathered into those nice boulders. This just sort of weathering away like a big lump. So not every granite's going to give you those boulders. Sometimes you look at a hill like this. If you showed me this picture of this hill, I wouldn't be able to tell you what kind of rock it was very easily. And then the third type of rock, of course, is metamorphic. And in Arizona, the metamorphic rocks are generally all the older ones, and they've all been pushed up. And so almost all of them have a nice foliation or lining up of the minerals, and that foliation or lining up tends to be vertical. So if you see an outcrop with something that looks vertical, then you're probably looking at the metamorphic rocks, the older metamorphic rocks. This is at Chiricahua Peak in Phoenix. And just again to go in Pinal County, here's by the sheriff's office on Hunt Highway. You can see how these things are sticking up, the Pinal schist there. And then the third thing is the structure. What kind of structure is prevalent in the area to give us, the last thing to go with the rock type and to go with the climate? Well, we have essentially two kinds of structures in the state of Arizona. We have the Colorado Plateau, which is uplifted sedimentary layers, and we have the Basin and Range, which is fault block mountains and basins. Most geologists put a transition zone in. All that means is it has a combination of those two different structures. So we have, the two structures. You notice there's a little X up on the top, the rest area on Interstate 15. First time I went there, I thought it was really neat. The next time I went there, it was degraded some. So it's been quite a few years. So I'm not sure how it is on that rest stop. But if you go to that rest stop, if you look to the east, you see the Colorado Plateau. If you look to the west, you see the Basin and Range. Here's a sign that they had there at the rest stop. It's right almost on the Nevada border. It's on Interstate 15 from between Las Vegas and St. George, Utah. So it has a description to tell you can see in the map where the little black dot is maybe. The Colorado Plateau looking east. This is what it looks like. There's the interstate. So you can see the rest area is up on a hill above the interstate a bit. So a little bit about the Colorado Plateau. It's uplifted horizontal sedimentary layers pretty much. Some of them, may be bent or twisted, but I just put a few things in that, sneak them in, some of the neat geological things that I didn't list as a 7. So we can go to Antelope Canyon and Page. There's uplifted sedimentary layers. The rock is sandstone. What does sandstone make? Sandstone makes cliffs. Rivers cut down, as this was uplifted, the rivers cut down through it, and we end up with, something really quite spectacular and the kind of thing that, people come here to see. So we have an uplifted structure. We have sandstone as a rock in this photograph, this location, and we have a dry climate. If it was a wet climate, we'd have a wide valley. We wouldn't have this narrow slot canyon. And then I always put Rainbow Bridge in. I know it's in Utah, but it's only a few miles across. And since ever I got to Arizona, I've always determined that Rainbow Bridge should really be in Arizona. And 99.9% of the people that go to Rainbow Bridge start out in Page, Arizona. So to me, it's an Arizona feature. And the thing is, to me, it's one of the most spectacular things around. And again, the rock is sandstone. It's critical. It's uplifted so that the river's cutting down. It's caused by the river. You can see how the river's cut. It had this, meander or loop in it. And then eventually, by grinding away over under the edge, it was able to cut through and form that bridge. And again, to me, it's one of the really neat kinds of geological things we see in the state of Arizona. Canyon de Chelly, just to show you some other uplifted layers, cliffs, sandstone, again. And then if we go back to our rest stop on Interstate 15 and we look the other way towards the Basin and Range, we see that the rocks have all been tilted. They've all been moved. This is standing there right by the interstate. That's the Virgin River there in the bottom. And you see everything's tilted. It's not uplifted horizontal rocks anymore. And as we go south in the Basin and Range, the tilting, the change becomes really dramatic. So around Phoenix, around Coolidge, Pinal County, the basins have dropped down 5, 6, 7, 8, 10, more than 10,000 feet, some cases, below the surface of the land, and the ranges are the uplifted parts. And you can see there's all these faults. So we call them fault block mountains, fault block basins. The basins here have not been carved by rivers. The basins here have been filled in by rivers. The basins here have been caused by the downdrop, the faulting, as this whole area was pulled apart. And what's really good, and I've put this in to show, you see all these aquifers, and that's how people could come here and live. All they had to do was, in Tempe, the stories are you could hand dig a well and get water to drink. So, you're out in this hot, dry climate, but if you dig a well or pump or drill a well, you're going to get water anywhere out in the basin. You don't want to drill it up on the mountainside. And just a picture to show you. I mean, so here it is, hot, dry climate, different kinds of rock. We don't know what kind of rock that is, probably granites and things, igneous. And these fault block mountains and basins and lack of vegetation, lots of bare rock, kind of thing we see. Well, for the second thing, I picked something, and most of you are familiar with it. You just maybe never put it into context. It's the fluid volcanic rocks, the recent ones. There have been some throughout the geologic history of Arizona, but from about 15 million years ago until Sunset Crater with 1,000 years, less than 1,000 years, we've had all of these fluid volcanic rocks, and they cover about 20% of the state of Arizona if you look at a geologic map. This is, of course, in the San Francisco Peaks. And this is what it would have looked like. I mean, this is Hawaii, but Hawaii has the fluid kind of volcanic activity. It's not very explosive. The lava pours out and runs. We have lots of evidence from looking at the geology around the state that there were lots of fissures. It's a fissure eruption, that this could have easily been a picture in Arizona. It could have been a picture in Pinal County 6 million years ago. We had this kind of activity here. Down by Gila Bend 1 million years ago, there's a giant volcanic field, and White Mountain, San Francisco Peaks, lots of places around the state, 20% of the state, this kind of activity. And the fluid volcanic rock comes from the mantle. So if you look at the right-hand side, the Sunset Crater, the rock comes from the mantle, comes straight up and erupts out. For the San Francisco Peaks, the magma starts in the mantle, but then it sort of gets slowed up and mixes up with some stuff in the crust of the earth. And so it's a little more viscous, a little more silica rich. So it forms a little bit, higher. It's not quite as fluid. It's a little thicker. So we get our composite type volcano then instead of our cinder cone or our, rarely fluid lava flow. We know this is coming from the mantle because we can find, there probably is half a dozen places around Arizona where you can find chunks of the mantle in the basalt. The most famous, of course, is Peridot Mesa up on the Apache Reservation. And it's incredible how much peridot, how much olivine is there. So all that green rock, that's the mantle. That's what the mantle looks like 15 miles, 20 miles down underneath there. And those are chunks that were brought up, with the magma. The mantle started melting. And as it melted, chunks of rock broke off and the magma moved up and picked up the chunks of rock and brought them up with it. And of course, being interested in minerals, I have to look at the peridot, which is really olivine, the mineral foresterite officially. And you can see it's, of course, world famous for, the gemstone. Another real common feature or famous tourist sort of place is Sunset Crater. 1060, 1070, 1080. I see a little conflict over the exact year now, but less than 1,000 years ago, it was active volcano, active cinder cone. And if you go to the visitor center there, they have some good stuff. And Pahoehoe and Aha, well, what are those? Well, those are Hawaiian terms because this is the kind of volcanic activity that we see happening right now today in Hawaii. And it's the kind of activity that we had here in Arizona during that time period, the 15 to present day. Present day meaning we could still have some volcanic activity from this kind of this type in the future. And this is a picture again from Hawaii. You see how this stuff is crystallizing, hardening, rolling along. Here's a picture of similar kinds of stuff by Sunset Crater. So same exact thing. I mean, it would have looked in Arizona just like we see in Hawaii today. Same exact things happening. SP Crater, maybe 70,000 years old. And I put that in because 50 years ago, when I first came to Arizona, you could climb up Sunset Crater, and now you can't because people were eroding it away. But you can easily find it. And again, the Arizona Geological Survey has some information. You can drive out. The road's not too bad, dirt road, and you're allowed to climb SP Crater if you really want to have that experience of, 2 steps up, 5 steps back as you slide up and down the cinders. I've taken my classes there when I was teaching, and then you can see the lava flow that poured out of the bottom. And then remember, when the magma mixes in the crust a little bit, it gets to be a little bit thicker. It's not quite as fluid. So we build up the composite volcanoes like the San Francisco Peaks. And of course, they're, the highest places in the state right now, these volcanic mountains. Government Cave Lava Tube, really a neat place. It's there, it's free. You can go, you can find out where it is. Take your flashlight and go in. I've taken all my grandkids there. I put this in because, again, another place you can drive out to the Grand Falls of Little Colorado. There's not always a Grand Falls, only in the spring or after big summer rains, but pretty spectacular. But the falls is there because of a fluid lava flow. The lava flowed out, moved the Little Colorado River around. So it had to fall back over the cliff into the canyon. The White Mountains are all the same. There's hundreds of cinder cones, literally hundreds and hundreds of cinder cones around the White Mountains. The main part of the White Mountains, Mount Baldy, again, is the thicker composite volcano, but there's fluid stuff, covers hundreds and hundreds of square miles. Casa Malpai is an archaeological site, but I just put it in because it's kind of neat, where all the buildings were built from basalt because that was, the local rock that was available. You drive to Flagstaff on Interstate 17, you'll see near Bumblebee, things like this. You can see there's a basalt flow on the bottom, and then it weathered, changed the soil. That soil didn't get eroded away. It's still there. So it must have been a little bit cooler and wetter than it is now. And then more basalt flow on the top. There's a road cut, so that's, artificial outcrop in a sense. And on the Beeline Highway, driving to Payson, as you go past, up towards Sunflower and stuff, just look around, look at all the boulders of basalt. I mean, it's pretty spectacular, really. That's all basalt that's breaking off the top and just rolling, sliding down the side. So, like I said, about 20% of the state covered with that type of rock. And of course, Pinal County has to come into it. So we have Poston Butte, which I'm standing on top of in the bottom picture, and it has a big F on it. And looking across, and that's Walker Butte, F for Florence, and the Walker Butte across the other side there has a big C for Coolidge. And 6 million years ago, this was a big fluid lava flow. Everything between here and there was lava, was basalt, the big lava flow that covered this area. Pretty local, but, over the area around, there's just a half a dozen little remnants left. Everything else has been eroded away. A couple of hills on the Hunt Highway have the basalt. And I put this in just to show you the faulting, the basin range faulting, the part of the structure. So, the lava flow flowed out flat over the ground 6 million years ago. Since then, there's been this motion, tilting, because the top of both of those buttes lines up if you go out and look at them. And so they've obviously moved over, sometime since they were a lava flow. Then the third thing I picked are the explosive volcanic rocks. And these are a little older. There are lots of them if you go back through the history of the state, but the recent ones are the ones we can see 15 to 30 million years ago. This is what they look like. Um, they're caused by something different. They weren't caused by this pulling apart from the magma coming from the mantle. They were caused by a subduction zone where the sedimentary rock, the sand and mud and stuff in the ocean gets subducted down, and a lot of seawater is subducted down. That sediment's full of water, and that melts up the material, and it eventually gets to the surface as these much more silica-rich, quartz-rich kinds of volcanic eruptions, and they're not fluid. They're very viscous or very explosive. So a different type of origin. And so the state obviously had a different geologic history 30 to 15 million years ago than it did from 10 to, 0 million years ago. And it would have looked something like this, perhaps, if I showed you a picture of what it looked like in Hawaii, and this might have been something that you would have seen in Arizona, standing in Phoenix or in Florence or Coolidge about 10 or 12 or 15 million years ago or 20 million years ago. You might have seen something like this. These most famous are the ones that most of you are familiar with, are the Superstition Mountains. There were three big explosive calderas. You can see the Goldfield one 15 to 16 million years ago. The Superstition caldera, the guy's hand is over it 25 million years ago. And then there's a third one that's over to the left. So these were giant eruptions. They were explosive. The material exploded out. It would have looked something like that, probably a lot worse, a lot higher. It would have traveled, all over across the country, most likely. These were pretty explosive, pretty violent type eruptions. Some people think they were as violent as anything we've seen, in recent times. Superstition Mountains. And the thing is, this type of more silica rich tends to make cliffs. So we talk about rock types. So the rock type, volcanic tuff or explosive volcanic rhyolite or, things like that, tend to make cliffs. And I have seen papers where people have gotten it wrong. They see these cliffs and they think they're sandstone because, if you go to Monument Valley or you go to the Grand Canyon, the cliffs are sandstone. But here in this part of the state, we have some sandstone. We have some sandstone cliffs, but we also have a lot of volcanic these explosive volcanic rocks, and they all tend to make cliffs too. So Superstition Mountains. Here's an outcrop. You can see layers of ash and rock that exploded out. And then there's a big chunk that exploded out, and obviously the layers weren't hardened. They weren't cemented together quite yet because it obviously made a depression in those layers. So that's a typical kind of thing. The bottom layer is pretty typical. You see all the fragments, and the fragments obviously can be all different sizes. The big one up on top is probably about 2 feet across. So a pretty good sized rock flying through the sky. Like I said, these rocks aren't as widespread. We have the Superstitions, Dripping Springs. The Chiricahuas are the same exact thing. Again, you can look them up, go to the Arizona Geological Survey. The tuff is a sort of a vesicular rock, a gas-rich rock, and if it gets buried, it gets squashed, so they call these flattened tuff fragments. But again, you can see it's a really hard rock. It tends to make a cliff. And a lot of the Chiricahua Mountains stuff, again, because as it cools, it cracks, and water can get down the cracks. And then here you sort of have alternating layers where some layers are a little more ash rich, and they're going to weather a little faster. And we get all kinds of pedestal rocks. Just a great variety, a fantastic place to go if you've never been there. And in Pinal County, here's a hill by the hospital. I can see it from my house. Basalt on the top, 6 million years old, tough, Next layer down, probably about 15 million years old, and then granite on the bottom. That granite's 1.4 billion years old, much older, but that gives you, an idea of what you can see. So that tuff is explosive volcanic stuff. It exploded out mainly as ash. The ash is hot, and so when it settles down, it kind of cooks itself together into a fairly hard rock. We can go see Pyrite and Superior. This was a big deposit of obsidian, so we think the volcanic lava erupted under a lake, under snow. Somehow it cooled quickly, formed obsidian. Again, over time, the water gets in, it devitrifies the glass, and these are like the granite boulders, except they're much smaller. They're remnants of the obsidian as the water gets in and changes the obsidian to perlite. So these are exactly the same thing. They're the product of the weathering, breakdown of the perlite, and these are the remnants of the original rock. And the volcanic rock's a good place to look for geos all over. There's some good geos that were south of quartzite down in that area. A lot of, again, you get the same volcanic rock there because you have gas bubbles and lots of gas in some of these rocks. The gas bubbles in the rock, of course, are obviously a natural place. If there's any silica solutions, then they can get into the gas bubble and start to deposit quartz crystals. Then I picked three, what I think are the most outstanding of the geological sites in the state. Probably Meteor Crater. There's no crater in the world, I think, that really shows the attributes of the crater meteorite impacts like Meteor Crater. Here's an aerial view. You can see the museum. The museum there is fantastic. I recommend it highly to anybody that hasn't been there as a really good place to go. Here's what Meteor Crater looks like if you're driving up to it on the ground. It's this lump and not very spectacular, but that's what it looks like. Now, the meteorite, they estimate, hit around 50,000 years ago. And it was thought from this picture, you can see that the meteorite might have penetrated into the ground and all the chunks of meteorite are underground there. Well, they're pure iron nickel. It's an iron nickel meteorite. So this guy Barringer put a mining claim on there to mine the iron nickel. And it's actually, Meteor Crater is still owned by the Barringer Corporation. I mean, it's privately owned. It's not a national park or a national monument. It's originally a mining claim to mine nickel iron. Oops. Oh, don't want to do that. Go away. Don't know how to do that. There we go. Again, 50 years ago when I first came here, you could walk down to the bottom just on your own by yourself. And so I did. And all the Barringer's mining equipment was still down there. It still is today. So this is the equipment Barringer set up. He put a shaft down in the middle of the crater to be able to find the iron nickel that was down under there. So it was a mining claim, and this is the mining equipment. And he put some tunnels in around the side at different places. But he found no meteorites at all digging down in the bottom of the crater. Well, it was determined that the meteorite, you can see it coming in, hit, it exploded, all of the little extra stuff around the top all got thrown out from the explosion, and the meteorite busted up and was scattered all over. And here's a map of where people have found the meteorite. So all the black dots are chunks of meteorite, and you can see and the size of the dot has something to do with the size of the meteorite. So the meteorite exploded, and it's obviously scattered over many, many square miles there. And of course, over the years, lots of metal detector people have gone there. It's illegal, but to find meteorites. I always heard stories when I came here about going on a moonlit night without a flashlight with your metal detector to find. I never did it. In the museum, here's one of the larger fragments that you can see.
Sadly, that's their museum, not ours.
Yeah. But it's worth it. They've done a really good job. Excellent. I mean, they really have. Petrified Forest, Painted Desert. I mean, there's petrified wood all over. I think people find it in every state in the union, or they claim to, but there's nothing like Arizona's. The Painted Desert is sort of name of the area with the Petrified Forest. It's the Chinle Formation, and it's a sedimentary rock, and it forms a slope, so it must be shale. So again, we see the same kinds of things. We see that shale doesn't make cliffs; it weathers into these slopes and rounded sort of hills. It's estimated 100 million years ago or so that this is might have what it looked like. There were swamps and lots of trees growing, and the trees were getting knocked over and carried in floods and buried in the mud. And then you see the little volcano over there sort of towards the left. Well, those volcanoes weren't really here in Arizona. The closest volcanoes were probably in California, but all that volcanic ash, it was a subduction zone, so it would have been the silica-rich stuff, the explosive stuff. The volcanic ash was all carried over here and fell down in these swamps too, because we need a good source with lots of good pure silica to replace the wood. And these are old pictures from the visitor center at the Petrified Forest. So the solutions with the silica-rich solutions go in and sort of cell by cell and structure by structure replace the original wood with quartz, with the mineral quartz. And if the quartz has a little iron, or if there's a little iron or manganese or whatever, a little bit of other elements, then we get some color. And that's just a typical view, nothing special. I just wanted to show you what it looked like, the clay, the Chinle Formation, the shale, the petrified logs, which of course are so much harder. So as the ground keeps lowering down, more and more logs will be exposed, and they'll all just lay out there. And one of the petrified logs, just to show you a cross section, I mean, that's why it's so special. It's such spectacular looking stuff. And since the first guys got there, they've been mining it to make stuff. This I took in Tucson probably 2 years ago, 3 years ago. There's private property all around, which obviously has some pretty big logs on it. So you can go there and buy yourself all kinds of coffee tables or end tables or whatever kind of a slab of petrified wood you want. These are all for sale in Tucson. Out of my price range, but there they are. And then finally, I think all of you really, the Grand Canyon, what's the place to go in Arizona to look at rocks or geology is the Grand Canyon. They have really good stuff. They have Geology Museum. They have Walk of Time now along the rim, South Rim, where you can walk along, and the steps are, so many million years. So a really good place if you're, trying to learn more about geology. So there are two parts that I put in here, a little bit about the geologic history and then a little bit about the formation of the canyon. And again, we could have at least a whole program or probably multiple programs just about the Grand Canyon. I did a class for Mesa Community College once just for the retired communities on the geology of the Grand Canyon. I think it was 3 or 4 2 or 3 hour sessions. So there's plenty of stuff to talk about. So you're going to get a quick overview. The geologic history, I just put this in to point out that we see lots of rock, but there's lots of missing rock where it says nonconformity. Between that rock and the rock on top of it, I'll show you in a picture, there's something like 1.5 billion years of geologic time missing. The angular unconformity is several 100 million years, and each of those disconformities is some hundreds of millions of years that are missing. So we don't have anywhere close to a complete record of geologic history or geologic time in the canyon, but we have a really great one of what we have, what we can learn there. The rock on the bottom there is metamorphic. You can see it sort of looking like it's vertical, going straight up and down. And then the sandstone makes a cliff on top. So again, rock type. And the age difference, the schist on the bottom, 1.7, 1.8 billion years. The sandstone, 500 million years. So not quite 1.5 billion years missing in between there of, what in the world is happening in the world during all of that time. And then you can go up through the layers. Again, you can see these different gaps in time. They're not obvious, but geologists, of course, study them, and there's tons of literature and guidebooks, and you can find out all you need to know. And I picked one rock, the red wall limestone, just to give you an idea about the geologic history. There's a map. You can see the ocean got deeper as you went out towards Nevada. And so, there's a positive area, Navajo, Apache County, and 0 feet thick, and then 800 feet over towards the Nevada border. That's the thickness of the layer. It's about 345 million years old, this particular layer. There's a picture of it. Notice along the top, it's a limestone. So over time, or when this was exposed earlier on in its geologic history, hundreds of millions of years ago, there's probably some karst topography, some solution of the limestone there on the top. So that's why I have that particular picture. Somebody's, of course, studied it. These are all the kinds of fossils, so they can take all these fossils, look at them, figure out, and then from what they find, they can say this is what it looked like if you could have gone back 345 million years and gone scuba diving. You would have seen this kind of stuff, in northern Arizona in the ocean. And there's a map, again, of what North America looked like. You can see where the Grand Canyon is. So it's shallow ocean. It's only several hundred feet deep because the red wall is not very thick. And you see there's that little piece of land sticking up there. And then you go out to the deeper ocean as you go west. So it would have looked like this. If you could go back in time, you would have seen this. Then the second thing is, how old is the canyon? How did it form? And great question. Geologists have been fighting and arguing and studying and trying to figure it out for a long time. This slide isn't great, but this came out from the Arizona Geological Survey in the last week or two. So I cut it out. I didn't cut out well because I had to enlarge it. But 6 million years ago, they're thinking the canyon only started. So that whole thing, whole Grand Canyon, they think has actually formed in the last 6 million years. And so that's pretty fast, really, considering, how much time we really have to do it. But again, it's uplifted horizontal sedimentary layers. That's the key to what we see. The interesting thing is, we look at something like this. So this is Horseshoe Bend by Page. That's the Colorado River. It's not to the canyon yet, but for a river to erode like that, and eventually there might be a bridge there if it cuts under and cuts through if the rock's hard enough. So the idea was that this river was probably meandering around on a relatively stable surface when the land started to go up. And as the land went up, the river cut down where it was. And so the meander was there, the land went up, the river cut down, keeping that, same meander. As the land was slowly going up, it was cutting down. So, we have some ideas like that about, part of the origin of the canyon. And this is an old picture from information in the canyon, but it's true. If you go to the south rim and look, north rim's much higher, 1,000 feet or so, and all the water on the south rim drains south, and the water on the north rim drains into the canyon. So the canyon's much wider on the north side, which you'll see. It'd be obvious to you if you went there and looked, and kind of thing we see. And then finally, my sort of special thing, my interest in life is minerals, Arizona minerals. We have a new book coming out next year. Some of you have probably seen the things about it, the mineralogy of Arizona. University of Arizona Press, so I have to put my ad in here. Lavender Pit in Bisbee, and I have a picture. It looks sort of lavender, but then if you go there and read the sign, it's named after Colonel Lavender, some guy, has nothing to do with the color. I take all my foreign visitors and friends that come to the Copper Queen so they can experience an underground mine tour. Kind of neat, I think, something special, different for Arizona. And we have mines and prospects. The Arizona Geological Survey probably has 10,000 mines, prospects in their files. I mean, they have thousands and thousands of files. Pinal County alone had like over 2,000 files, for the county. And right now we're up to 982 mineral species. That's how many we're going to have in the new book, 982. And what I'm going to talk about tonight is mainly the ore minerals, because those are the ones that people want to find because they make money finding the gold and silver and copper and lead and zinc. And then the collectible minerals, the minerals that the mineral collectors want. And of course, every rock in the whole state from one end to the other is made up of minerals of some sort or other. So I'm just mainly going to talk to you here real quickly about the ore minerals and the collectible minerals. So the first thing that forms is sulfides, pyrite, chalcopyrite, bornicline, things like that. There's a whole story, and that's a whole different talk that I have about how you leach these metals out of basalt in the ocean and subduct them down and put them back up. So I don't know, some of you may have heard my basalt to wolfinite talk, and maybe I can regenerate it someday, do it again. But anyway, sulfides, which are the things we're going to see first. And the most common of them would be pyrite. So it's iron sulfide. So we have some nice pyrite in the state. And I think the thing is that, we look at the neat canyons and caves and arches and bridges and pillars and pedestal rocks and all those things, but the minerals are so spectacular too. I mean, nature makes these things that to me are just wonderful. The fact that these crystals can grow and you can end up holding something like that in your hand. So pyrite, iron sulfide. So it's iron and sulfur. That's all it is, those two elements. And it's the most common of the sulfur-bearing minerals. Galena, the silvery stuff in the center, and lead sulfide and sphalerite, the dark piece on the top and the bottom, zinc sulfide. Most all these pictures are from Jeff Scoville. I thank him greatly for allowing me to use them. He does such a fantastic job showing, what these things are. They're real beauty. So it turns out sulfur is unstable. You add oxygen, you add water to sulfur, you get sulfuric acid. In fact, sometimes it's a problem. It's called acid mine water, but it's a natural thing. It happens naturally. There's pyrite. If you take pyrite, throw it in a jar of water and put it out, and or the air in the air, it'll start to break down, and you'll start to get sulfuric acid. Again, it might take thousands or millions of years, but the point is it happens. And once you get the sulfuric acid dissolves most of the other minerals that are present. So I don't know if you can see in the center, it says iron Hattergossen. So everything's dissolved out of there except the rust, the iron oxide. Because if you ever have rust or iron oxide on your car, excuse me, you know how hard it is to get rid of it. So everything else is leached out. It's gone. Except for the iron and gold. Gold's not soluble, so gold might be left if there was any. And then if the acid gets neutralized, we start to precipitate out all these wonderful minerals. And they're mostly carbonates and silicates, lead carbonate, copper carbonate, zinc carbonate, zinc silicate, copper silicates, things like that, chrysocolla you see there. And you might get cuprite and even native copper as you go down. And when you get to the water table, below the water table, the oxygen's gone because the pore space is all filled with water. And some of the copper starts to precipitate out there. And so we have these secondary enrichment zones. which are actually richer, and then eventually you go to whatever the original sulfide ore was. So um, that's the zoning in the ore deposits, and it's pretty spectacular kind of thing. In Pinal County, we have the Sacaton mine. Right now, they're talking about calling it the Cactus Mine. Some people are trying to start it up again, I think. I've been reading lately. But at the very top there, you see that reddish area. That's leached out iron oxide. Then you see the blue area. That's the oxide zone. And then below that, you get the enriched zone. Well, there's no water there, but the water table was much higher in the past. But as the climate dries out, of course, we have, water table would be dropping, and the miners probably pump some water too. Chalcocite is extremely rich. It's a copper sulfide, but it's about 80% copper. So, if you have a mine with a rock that's 80% copper, it's worth getting. And that's the thing. The first guys came out here, most of them would dig down. They would dig down here and skip the top zones and just go for the enriched zone and take that rich ore out underground. And then they'd leave. That would be the end of it. And then, of course, with the modern technology, we were able to open up and start mining, giant scale, these large scale. So now they mine the primary ore too, which is, maybe just 0.5% copper, very low amount. But, if you can mine millions of tons of it, you're okay if you can set up the technology. The oxide zone, so that's the stuff, the sulfuric acid, as it gets neutralized, it starts to deposit these different minerals. And in the oxide zone, there are several hundred different minerals. It's the ones the collectors normally really like, and you'll see as we look through here. And then inspiration, I put that in just to show you again the oxide zone. So the early prospectors look for these rusty areas. They find a rusty area and they start digging a hole, see what they can find underneath. So azurite, malachite are copper carbonates. So as the copper goes into solution and then it, slowly goes down, if there's a space, and it can grow. And of course, we have the most incredible azurite and malachite specimens in the state of Arizona. I mean, if you look at something like that, to me, it's just incredible, just amazing. Chrysocolla is a copper silicate. So the whole rock there is chrysocolla, and then part of it got covered with the druzy quartz with the quartz crystals. It makes it, look really, really good. Cuprite is copper oxide on malachite from Bisbee. Nice big octahedral crystals. Cerussite is lead carbonate, so we have copper carbonate, lead carbonate, flux mine. Orichalcite's a copper and zinc carbonate, the two together with the carbonate, 79 mine. Again, these are all Jeff's pictures. Smithsonite, zinc carbonate. 79 mine's pretty famous for this green smithsonite. It's not very common in the rest of the world. Hemimorphite, zinc silicate. Chrysocolla is copper silicate, so we get, these various silicates. And then turquoise. Turquoise is not as common as copper aluminum phosphate, so we have to have the phosphorus of Arizona, and literally tons have been found, but if you look at the billions of tons of ore that have been moved around the whole state of Arizona, over the last 150 years or more, then, the thousands of tons of turquoise are pretty amazing, but just part of the whole deal. So the prehistoric people, used turquoise, and the first guys that showed up here, Spanish, found some turquoise, and then of course the English started looking for the turquoise. A couple of Native American or prehistoric turquoises as a pendant or a bracelet. And then some of the modern turquoise, Sleeping Beauty mine near Globus produced a lot, Kingman produced a lot. And then we have some other minerals. So wolfinite, and of course, I tell a lot of people well, our state mineral is wolfenite. And of course, most everybody looks at you, well, what in the world's that? And they all know what turquoise is, but, nobody, which is a state gemstone. But, if you're not a mineral collector, what in the world is wolfenite? So, here's an exhibit that was in Tucson to promote wolfenite for the Arizona State Mineral. In 2017, Governor Ducey signed the law making wolfenite the state mineral. There's, again, one of the classic red cloud wolfenites, just unbelievable, wonderful stuff. And just to show there's other stuff besides copper mines and lead and zinc mines. Real quick, really famous, of course, place is Four Peaks Amethyst Mine in Arizona. If you have money, you can go up there in the fall. I don't know if they're doing it this fall, but they have over the last few years. For some hundreds of dollars, they'll take you up in a helicopter, set you down there for a couple hours, and let you pick up carefully, not the best stuff, but some things. And it's really famous because it tends to have kind of a red tint to it. So it's really quite different. And then, of course, there's all the gold in Arizona. And that's a whole talk, gold in Arizona, I think. So I just had to show you that. So, we can all go out and look for our gold nuggets. They're out there. I'm sure there's more to find. And that's it. So hopefully that enlightens you a little bit. I know that it's quick and it covers a lot of territory. I mean, it's several weeks worth of Arizona geology class, but like I said, if you're really interested, go looking, and just Arizona is so wonderful. There's so many geological wonders in the state to see. So if I move this, will you see me then, Bob?
I see you now. And so do our viewers.
I can get rid of that. And there I am. Now yourself.
All right. Well, thank you very much, Ray. That was fun talk. You stole a lot of my pictures. No. The slideshow that I had put together that I couldn't show because
you can still do it. There's no problem.
Oh, of course I will be. I will.
Absolutely.
I'll say it aloud. If you have a question, please put it in the comments, and I will do my best to ask Ray before he has to go. And there's a comment. So let's see. Ken Elliott and Annalena Seahill say, excellent presentation.
Thank you.
And okay, well, I guess there are no questions. Right. You did too good a job as usual.
Right, yeah. Everybody's falling asleep, whatever.
Yeah, though we've just been bombed. There, I did. Okay. Well, I thank you very much. I will, let's see, I want to put something up here. I'm sorry, folks. I'm having a terrible time. There we go.
Little plug. Yeah, if you're just watching this and you're not on our mailing list for our emails, our newsletter, go to Pinal geologymuseum.org, the website. Bob's worked really hard to update it. It looks great. Go to the website. You'll find out, how to contact us. And I'll be more than happy to put you on our newsletter for future programs, for field trips, for meetings, whatever kind of things we'll do in the future, because we're relatively new in the state, but I think we have some great potential for good things to do yet.
Yeah, and we're all over social media. We have Instagram, we have Facebook, we have Twitter, so you can find us on all of those things, as well as YouTube and our other